There we go. Get the video started. I don't have the wheel of death. That means I guess the audio is working, but sometimes the wheel of death shows up in about 3 seconds. So 1, 2, 3. I think we're set to go. All right, so this video is about getting a feel, numerical feel for the product rule. Product rule will come to you pretty quickly, maybe not on the first or second look, but 2 or 3 days from now, you should be able to apply the product rule to basic elementary functions. Gets a little more complicated when we do the chain rule. Which I want to do a video on very soon because that opens up the door to all kinds of discussions. But first, let's get a feel for the product rule. Let's start with y equals x to the fifth. At this stage of the term, we should know how to take the derivative of that, 5x to the fourth. But I could express x to the fifth as x squared times x cubed. And so therefore, the derivative has to be the same since they're equal. Step one. Step two, going back to day one, we're going to use our model that really opened the door for Sir Isaac Newton, was how does the area of a square change at an instant? And it's a layering process, right? The next biggest square minus the one inside, he did a squeeze where he looked at, square area 3.99 and then 4.01, and he looked at the numerics of that. And he realized there was a pattern there of twice the x value that you're working with. We showed that on the first day. I think over here, I'll just show the numerics of that, bringing you back to day one. So we look at 3 squared 9, 3.001, 9.0601. We played with this number a little bit. We got more accuracy with 3.0001. being 9.00060001. And if you take the change in x, ignore the cusp, divide by 0.0001, we get a 6-to-1 ratio, which is twice the x value. All right, so we covered that in day one. All right, and we talked about tangent lines. And using grandma on Route 91, 3 hours from now, she's 9 miles north of the Vermont border, traveling at 6 miles per hour. So that's why we study math, because we know we got to go save grandma. Not Route 91 being your y-axis, north-south. All right, so that's just bringing us up to speed. So the picture again that Newton worked with was the change in area. The change in x is represented by dx. In our case, that was represented by 0.01. This is the x value 3. And so that new area is 0.03, right? And then same thing happening here, 0.01, x value 3. 0.03 is the area there. And those two layers add up to 0.06. 0.06 divided by the change in x, 0.01 gets us that 6-to-1 ratio. So we played with those numerics. We're now going to change this to looking at, and that was this, you can pause the video and just look at that. And those are the symbols that go with what we did, because we're not going to carry squares around in our pocket. So now, I'm going to play with this, the numerics of this, if the sides of the square change. Obviously, this is a rectangle now, different side lengths. Could be some moments where it's square lengths. We said x squared equal to x cubed, but I'm not sure where that's going, so I'm not going to deal with that. But we're going to look at the accumulation of area here of the layering process. That's your change in area. And we're going to actually do it with some numbers. So let's see. So we're going to stick with the number 3. So 3 squared is 9. 3 cubed is 27. So we have an original, did I cube? Yes, I guess I put those in table values over here, running out of room on the lab table. I'm in the lab room. So 3 to the 5th is 343. And so I guess that's this area of this rectangle, 343. And if I change my x to 3.01, I get a new area of 247.077 with some more decimals. Okay, some gross approximations here. And if I look at how this changes, right, when I put 3.01 in, well, we know that it changes actually by 3.01 gets us 9.0, the longer side now becomes 9.0601. And if I change the longer side down here, when I cube 3, I actually get 27.270901. Okay? We're just going to do some gross approximations and say that my change here is 0.06 and that my change here is 0.27. Obviously, I have to blow this up so you can see these numerics at work. Now, what's the change in area of the top layer? 0.06 times 27. What's the change in area on the right side? 0.27 times 9, right? That's the old, so 0.27 times 9. All right, this gets me 1.62. This gets me 2.43. And so if I add that up, I guess you can see this, I get 4.05 of new units of area. Okay, and that's my change in Y. So that's my change in Y. Right here, that's my change in Y. The new area, that's this layering of change. Okay, because I've got an area rectangle that's slightly bigger, and I'm looking at it, the change over a small interval of change in X. Well, you know, I can divide this by dx. Of course, it's not equal to that anymore, unless I divide this by dx. Now, what was our dx? Well, our dx was 0.01, which is really 1 over 100, right? And so if I actually do this calculation, then I get 405, right? So at x equals 3, my function x to the 5th, oh, wow. Boy, did that come out nice, even with just 0.01, some gross approximations. That's interesting. So what really happened? Remember, you can pause, critically think about this, take more time. I'm flying through it right now, just so I can get a video up. You know, you can replay different instances of what I'm talking about to get a feel for what's going on, because if you don't have a feel for the numbers, I doubt you have a feel for the product rule. So what really happened? Let's see, where am I over here? Oh, yeah, so in the 3 by 3 x squared model, you know, this was 3 by 3, 3 by 3, then the change in x was 0.01 times, you know, it's 3 and 0.01 times 3, you know, getting your 0.06 divided by 0.01, your 6 to 1 model. But this was just for x. This is different. When I'm looking at x squared, that really changed by 0.06. Well, that's really 2x dx. That's really 2 times 3 times dx, which is 0.01. That's really the side of the top layer. And the bottom layer, did I do it over here? No, I already talked about that. The bottom layer over here was x cubed, and that really is 3x squared dx. You know, 3x squared. It's not just changing by 0.01, it changed by 0.27. That length changed by 0.27, which is 3x squared, right? Divided by 0.0 or times 0.01, right? 3x squared, derivative. That's how this is changing. It's really a new axis. It's really a new axis, okay? And on this axis, when I put the number 3 in, and I put then 3.01 in, I didn't change by 0.01, I changed by 0.27. It's that number squared times 3. All right, and that's really what's going on here. So I think I would have liked to have said that a little more clearly, but let's go over here and look at what happened. Okay, so that, did I get a drawing? Yes, I did, good. So this precedes that, and let's see if we can follow along. Oh my God, I never really checked to make sure that the camera was clearly on everything I'm talking about. I hope so. And I'm not doing this again, I don't have time. So the side x squared really changed by 2x dx. And so the new area here is 2x, it's commutative, right, or associative. I can rearrange multiplication. 2 times 3 times 4 is 3 times 2 times 4. So I can rearrange I can do 2x times x cubed times dx. 2x times x cubed times dx is the top layer of new area. 3x squared times this side length is really x squared, right? That side length's x squared. So 3x squared times x squared times dx. And that's the new area, the change in area. Okay, the change in area, I don't want to butcher this because I might come back to it. So the change in area is this layer, which is 2x x cubed dx, and this layer, which is 3x squared dx. And of course, you know, if I put the numbers in again, I get 6 times 0.27 times 0.01, 27 times 9 times 0.01. I get the 1.62, I get the 2.43, the 4.05, and that's the change in area. Okay, way down here. So I get 0.01 times that, which is 1.62. I do the math there. I get 2.43. So this is really 1.62. I'm getting rid of it now. When x is 3, and this is 2.43. All right. Now, what can I do with this to get the rate of change of the area with respect to x? Again, I come in and divide by dx. I divide by dx, dx being 0.01. So multiplying by 100 gets me an approximation of 405. I mean, I've gotten rid of some of the decimals. I'm just grossly approximating. Okay. What was the derivative of x to the fifth? Y equals x to the fifth. What was it? It was y prime was 5x to the fourth. And if we drop in x equals 3, we get 3 to the 4, which is 243. 3 to the 4, 81, sorry. 27 times 3, 81. And 5 times 81. Oh, it's a good thing I said that because that's 405. What does that 405 represent? It represents the rate of change at 3. We're at x to the fifth. 3 to the fifth is 3 to the fourth, 81, so 243. Okay, and what was when I drop in that? 405. So what's the equation of the tangent line? 405 times x minus 3 plus 243. So in our grandma traveling on Route 91 analogy, what do we have? We've got her going at 405 miles an hour. 3 hours from now, 243 miles north of the border. She's well into Canada and heading north at a pretty fast clip. I don't know how she's driving that fast, man. That's a woman. Sometimes she's going 6 miles an hour, sometimes 405. Again, we better talk to grandma. All right, so almost to the product rule now. I think I can turn this around. Yeah, here we go. So x to the fifth, which is 5x to the fourth for a derivative, we could express x to the fifth as x squared times x cubed, y. So what is dy dx? It's 2x times x cubed plus 3x squared times x squared, which is equal to 2x to the fourth plus 3x to the fourth. And what is 2x to the fourth plus 3x to the fourth? Oh yeah, 5x to the fourth. So where did 2x come from? Looks like it's the derivative of x squared times x cubed, the other side of the rectangle. And where did 3x squared come from? No, that's the derivative of x cubed times the first function. So I guess if g of x equals some product of one calculation times another calculation, then it looks like the product rule is take the derivative of the first function, multiply it times the second function, and then add the second layer of area, the derivative of the second function, times the first unchanged. There's your product rule. Let me do it again, because I didn't have this down here. So if we have a function that is a product of two functions, then taking the derivative of that product means that you take the derivative of the first function, just like we did here, times the second function, leave it alone. Then we take the derivative of the second function, which is 3x squared, times the first function, f of x. That's your product rule. Okay, so we will do a very quick product. Once we get a y equals a product of the first times the second, so y equals sine x. Let's do it. Reads better if I do x to the fourth times the sine of x. what is the derivative of this calculation? We take the derivative of the first function, 4x cubed, and we multiply it times the second function, unchanged. Then we take the derivative of the second function, the cosine of x, times the first function, unchanged. That is the product rule. Now, gets a little more complicated when we do the chain rule, which I'm going to bring your way very shortly. Very shortly. Boy, did I even show that? Because I forgot to move the camera. This thing's backwards. All right, so I got to do this again, I think. So let me erase this, find my eraser, which is right here, not too far away. I'll do it again. So if we had a product, I'll do a different one. And now I'll do the same one. And we had x to the fifth times the sine of x. All right, then what is the derivative of that? There, I think you can see. The derivative of that is take the derivative of the first calculation, which is 5x to the fourth, times the side length that is not changing. And then add to it the derivative of the second function, which is the cosine. We've looked at that in class. Times, don't change the first one. Okay, so in essence, if y equals f times s, then y prime is f prime s plus s prime f. And that's what you'll see on your cheat sheet. Okay, so I hope that that didn't get butchered too much in terms of my forgetting to move the camera up and down. Ooh, by getting dizzy. There we go. All right, but you know, grandma's going 405. That's scary. All right, I'm going to close this out. You're going to look at it for homework. And now we've added the product rule to our list of things we're doing in class. Ciao, ciao.